Hello there. I'm glad you made it to this little island of quiet. Let the room be dim, the blankets familiar, and your breath unspool like a slow ribbon. Tonight, we'll cradle a tender idea. If a universe can be understood by simple rules, could we simulate one of our own? We won't force anything. We'll start with nothing, set a few gentle laws like tiny night lights, and watch a newborn cosmos flicker into being. Pixels of space, a rhythm of time, a hush of chance, then matter gathers, stars learn to glow, and stories wake. We'll move at the speed of comfort, letting each step settle before the next, the way a porch swing finds its rhythm. If this quiet keeps you company, a light touch on like and a soft subscribe helps other travelers find their way here. No rush, only when it feels right. For now, feel your shoulders soften and your thoughts drift like dust in a sunbeam. Close your eyes if you wish. We'll build our little universe together, unhurried and warm, one calm breath at a time. Imagine a blankness that isn't empty at all, a quiet room where possibility waits like breath before a word. In that calm, the brush is not bristle and paint, but a small grammar of rules. You don't paint trees or clouds. You set gravity in motion. You let gas learn to flow. You whisper to time to take careful, even steps. What rises on this canvas is not a picture, but a rehearsal, an attempt to coax the universe to act out its own story inside a patient machine. It isn't a dream of plugging into some neon matrix. It's the soft, grounded craft of taking laws we trust and letting them play together over vast distances, often billions of light years away. When scientists say simulation, they don't mean a pretty loop of computer imagery meant to dazzle the eye for a moment. They mean an experiment told in mathematics, a world built from equations where ideas can be tried, mistakes can be kind, and curiosity can rewind the clock as often as needed. Inside this quiet sandbox, knobs turn without drama, a variable slides, a history is replayed. The mix of ingredients changes the way galaxies gather, the pace at which stars are born, the length and grace of filaments that lace the dark. It sounds abstract until you watch a small clump condense into a spiral or see a void widen like the hush between heartbeats. Then the abstraction feels strangely familiar, like recognizing a silhouette in moonlight and knowing the face without seeing the eyes. Even so, a simulation is not a photograph. It's closer to a careful sketch drawn from memory, the memory belonging not to a person, but to physics itself. Every structure you see, from a dim halo to a bright disk, is the consequence of rules declared at the start. Gravity decides who dances with whom. Gas decides when to cool and when to rush. Light decides when to carry energy away. Instead of chalk dust on a board, these rules live inside supercomputers that hum for days or weeks, stepping through time in small, steady ticks. In other rooms, simulation means spectacle. A wave in a film can crash with convincing foam and never once obey the strict arithmetic of fluids. No harm in that. Its job is to please the eye. The scientific version keeps its promises to nature. If a galaxy spins too fast, if stars crowd where they shouldn't, if the pattern of clustering disagrees with what telescopes whisper from the dark, then beauty does not matter. The model is wrong, and the rules must be tuned again. This is the edge where art and discipline meet. Imagination chooses which forces to honor, how to mark time, how to give gas a body, and gravity a voice. Observation draws the boundaries. Telescopes, satellites, and detectors speak softly but firmly, setting limits the simulation must respect. It's a little like composing with a limited scale. There's freedom, yet the permitted notes are few, and the melody must fit what the sky has already sung. To begin a universe in code, you start with a gentle echo of the beginning. Not a literal bang, but an initial field, a cloud of particles scattered across a virtual volume. There may be millions, sometimes billions. Each is not an atom or a planet, but a stand-in for a vast share of matter, perhaps the heft of a small galaxy or a sprawling breath of gas. Then you let space expand as it did, and you let gravity pull as it must. Time advances in small steps, fractions of a million years, then another fraction, and another, while the computer calculates how each piece tugs every other. Patterns arrive almost shyly at first. A faint gathering here, a thinning there. Filaments stretch like sponge sugar between knots. Voids open like quiet plazas. Look long enough and a web appears, not drawn by hand, but teased out by rules alone. It resembles the map astronomers assemble from surveys, where real galaxies trace similar threads across the deep. Skepticism has its rightful place. If the beginning is invented, what justifies the ending? Comparison is the answer. The digital sky is held against the real one. Do the clusters form where they ought? Do voids have the right emptiness? Does lensing the way gravity bends distant light agree with the strength and shape of the structures in code? When the mirrors align, confidence grows. When they don't, the quiet joy of revision begins, and the recipe is adjusted with a steadier hand. Every success is limited by the laws included. Leave out a force you don't yet understand, and the world you build will keep the omission like a secret. Dark matter's nature, magnetic fields' mischief, the exact temper of early star formation, each unknown leaves a flavor that doesn't quite match the sky. The cake rises because gravity insists, but you taste what's missing. In that sense, a failed run is a gift. It points to a gap, a place to look harder. There's also a freedom here we don't have in nature. The real universe will not oblige a retake. A simulation does, tenderly. You can try a slightly stronger gravity. You can let the early fabric be a bit smoother or more lumpy. You can quiet the fury of black holes or let them speak a little louder. Each run is a what if, a way to ask how the present might be the child of many possible pasts. Not every project aims at grandeur. Some decide the night is better understood by a single lantern. A lone supernova, a turbulent knot of gas surrendering to a forming star, the inner weather around a hungry black hole. These smaller scenes teach the feel of the larger play. The same patience appears in other fields too. Earthquakes rehearsed in code, weather teased into tomorrow's shape, climate stitched from currents and clouds, quantum habits explored where lab lights cannot yet reach. The uniting principle is simple enough to fit in a whisper. Build a world from math and see how it behaves. Ingredients come before recipes. Before galaxies have spirals, there must be something to spiral with. Before mass is allowed to gather, its behavior must be declared. Before time can pass, a clock must tick. The rulebook is physics, and the language is mathematics. Soft on the ear, but precise on the page. At the base are particles, though the word is a courtesy. These are packets, each representing a large share of matter. No picture clings to them. They are numbers, with places 3 coordinates in a volume, and with qualities that change as the story unfolds. Position and velocity are always there. sometimes heat and chemical makeup too. On their own, they would drift without incident. Forces give them meaning. Gravity is the quiet architect. Over long spans it sculpts the whole, coaxing matter to fall together, merge, and settle into structures that endure. Most codes treat gravity with Newton's patient rules. A few, for special purposes, lean toward the full depth of general relativity, though the cost in computation grows heavy. With many particles, the number of pairwise tugs would explode, so the machine borrows cleverness from nature. A tree method groups distant masses into single voices, so a faraway cluster acts as one chorus instead of a million soloists. Near neighbors are resolved with tenderness, distant crowds with useful approximation. Electromagnetism adds color to the motion of gas. Hot clouds glow, shedding energy as radiation. Cooling changes pressure. Pressure shapes flow. Magnetic fields wind through these regions like invisible threads, guiding charged particles, stirring turbulence, nudging the conditions for star birth. On galaxy-wide stages, some details are softened to keep the dance manageable. In focused scenes, star nurseries, shock fronts, those details matter, and the simulation sharpens its gaze. Hydrodynamics gives gas its body. In space, gas behaves like a fluid, rushing into wells, shocking and shearing, rolling into eddies. One gentle technique, smoothed particle hydrodynamics, imagines the fluid as overlapping blurs, each particle's properties shared with its nearest company. The messiness of real flow, compressions, shocks, swelling and collapse enters the code through equations that know how pressure speaks to motion. Dark matter takes its silent place. It neither shines nor absorbs light, but it carries most of the mass and answers gravity with devotion. In code, it is another family of particles, unfussed by electromagnetic fuss, passing through one another without friction, gathering into halos that become invisible scaffolds. Ordinary matter nests within these halos like pearls finding their shells. Dark energy is quieter still, not a particle, but a pressure woven into the expansion of space. It is included as a change in the cosmic tempo, altering how quickly the fabric stretches, which in turn sets when and where structure can take hold. A subtle hand on the clock can change the entire choreography. Equations hold everything together. They are not small charms, but long, coupled sentences that tell how motion, heat, light, and gravity answer to one another. Time is sliced into careful steps. Too large, and the world stumbles. Too small, and the journey takes forever. Somewhere between is a pace that keeps faith with both truth and patience, and much of the craft lies in finding it. Beneath these forms lie constants that set the scale, the speed of light, steady and strict, the gravitational constant, quiet but universal, Planck's constant, small yet insistent in the places where the very small matters. Change those numbers and the melody becomes a different song. Because nature is richer than our budgets, approximations enter with humility. Not every supernova can be modeled atom by atom. Not every cluster collision resolved into every shock and spark. Subgrid models stand in for the unresolved, rules that say, here is the energy a burst returns to its neighborhood. Here is how a stellar wind might stir the nearby gas. These choices are tuned against observation, and tiny nudges can ripple into large differences later. There is art in this calibration, but it is honest art, measured against the sky. Out of these cold bones, warmth arrives. Step by step, galaxies curl into arms. Clusters approach and bow into one another. Voids deepen like held breaths. The result is not a universe of atoms, but of code that behaves as atoms would, and the kinship is convincing enough to rest your mind on. A simulation is not proof of creation, it's evidence of understanding. It tells us our few rules, carefully combined, can sing something very close to the same song the stars sing. Not so long ago, in cosmic terms, such projects were dreams with shoes too big. Machines were bulky and slow. The hunger for insight was faster. In the 1,960 seconds, a few restless minds tried anyway, and 1 second. They arranged a tiny number of particles, sometimes fewer than 10, sometimes only dozens, and watched how gravity nudged them. The picture was primitive, but a truth peeked through. Left to itself, matter refuses sameness. It gathers, it threads, it leaves quiet between the knots. The 1,970 seconds brought N-body experiments into clearer view. The N was simply how many bodies were allowed to speak to one another through gravity. Hundreds were possible, and that was enough to show a hint of the web. No gas yet, no stars, no dark energy, only gravity, purely Newtonian, doing what it does when given time. Complexity rose from simple beginnings. The universe did not need to be told where to draw filaments. It found them. Grids entered the scene when space had to be given a place to flow. Divide the volume into cubes. Let mass and energy move from cell to cell by rules of fluid motion, and add gravity's pull to keep the story honest. In the 1,980 seconds, hybrids emerged, grids for gas, particles for mass, and the first recognizable strands of the cosmic web appeared on screens. Clusters glowed at the crossings, filaments stretched between them, and wide, quiet voids made room for everything else. A missing actor changed the play. Dark matter, suspected because galaxies spun too fast to be held by visible mass alone, took its seat. In simulation, it behaved like a patient ghost, unseen, unlit, answering only to gravity, and it formed halos like invisible shells. Inside these, the bright parts of galaxies found their homes. This was a turning point. Halos gave the model its bones. Ordinary matter supplied the flesh. Through the 1,990 seconds and onward, power grew. Millions of particles became billions. Dark matter and gas could be followed together. Shock waves rolled. The highways of structure arched across the volume with a familiarity that made astronomers tilt their heads in recognition. Initial conditions became less guess and more record. The faint afterglow of the beginning, the cosmic microwave background, offered a baby picture of the universe. Small fluctuations in that glow were translated into initial ripples of density and code. The question became tender and bold. If you start with this infant, do you arrive at the adult we see now, roughly 13 billion years later? Universe in a box became a friendly phrase. Choose a cube, perhaps 100 million light years on a side. Fill it with virtual matter. Give it an honest expansion and let it live. You haven't modeled everything, but you've modeled enough to gather statistics, to witness how halos merge, how galaxies fall into clusters, how emptiness carves its broad rooms between the dense. These boxes helped confirm the cold, dark matter picture of structure formation and gave a place to test how feedback from stars and black holes shapes the bright parts we can see. The gift wasn't the spectacle. It was the freedom to try histories the sky won't replay, turn the dark matter up or down, ease the expansion, let stellar winds blow harder or rest, ask black holes to murmur or to speak with heat. Press, run. A different cosmos unfolds, and in the contrast, the logic of our own becomes easier to feel. The first attempts wore their seams on the outside. Pixels were fat. The physics was narrowed to what the machines could bear. Assumptions did more lifting than anyone liked. Still, a footing held. Gravity can fold simplicity into filaments. Code can slow the grand and bring the far near. What began as blinking points became a quiet practice of listening, letting models talk until the sky seemed to nod back. Some nights, it feels like tending a small fire. Feed it equations, mind the constants, tilt the grate so air moves just enough. In that glow, a universe gathers itself, not because we command it, but because we've learned how it prefers to move. The mismatch between code and cosmos, inevitable, honest, doesn't mark failure. It marks tomorrow's questions. Humility helps. The most faithful scenes grow from a short, repeated kit. Particles to carry mass and light. Forces to say how they meet. Equations to keep score. Time stepping forward in careful ticks. A handful of constants that never change their minds. Everything else, the spirals, the clusters, the wide, clean rooms arrives because simple rules, given patience, are generous with surprise. Eyes adjust. The room quiets. On the screen, a digital galaxy finds an arm. A cluster exhales a shock through its heart. A void deepens like the breath between notes. No trickery in it. Just a mirror polished by care. Where image and observation agree, understanding has found ground. Where they don't, wonder has a trail to follow. In that soft exchange between known and not yet, a handmade universe turns code all the way down, physics all the way through, steady as a heartbeat, warm as a whisper. And then, a room of humming fans in the early 2000s. A small circle of patient minds decided to grow a universe for real. Not a movie, not a thought experiment tucked into a notebook. The Millennium Simulation took form. 2005, Max Planck Institute for Astrophysics. Structure traced from about 380,000 years after the Big Bang to now over 13 billion years of quiet gathering and grand rearrangement. 10 billion computational particles in a cube, roughly 2 billion light-years across, each a heavy packet of dark matter. Time advanced in measured breaths. Gravity spoke. The whole thing moved like a slow numerical ballet, and the screen answered with webs and knots that looked suspiciously like what the night had been telling us all along. The output did not arrive as a pretty picture. It spilled out as petabytes of numbers, positions, velocities, and times like rain on the roof. Then came the gentle work of turning numbers into something the eye could follow. Filaments lifted into view, clusters lit the crossings, and wide, patient voids opened between them. The picture was not perfect. It was never meant to be. The Millennium Run modeled only the dark framework, the silent majority that shapes where bright things may live. Ordinary matter gas, stars, the glowing events we name was added afterward with semi-analytic recipes, careful guesses tuned against what telescopes had already told us. What made this digital universe feel alive was its usefulness. Astronomers could stand inside it with a virtual telescope, aim at a patch of simulated sky, and count what appeared. Those mock observations could be compared to real surveys. If the simulation undercounted galaxies here or overpredicted clustering there, it was a clue. Perhaps the feedback from stars was misjudged, or the starting ripples needed softening, or a knob on the expansion history was set too high. In these quiet trials, the cold, dark matter picture found its footing. Warm, dark matter, whose faster motion should smear away small structures, couldn't easily produce the crisp web seen by real instruments. Gravity, slow and stubborn, was enough to lay the lattice. The bright world would drape itself upon it. Scale was both triumph and limit. A volume so big could hold a fair sample of the universe, but its vision was coarse. Each particle stood for mass, far larger than a single galaxy. Small companions and fine textures were blurred. To see the delicate, scientists would need to trade breadth for detail. Yet Millennium proved something gentle and enduring, that a digital cosmos could be honest and manageable at once, and that beauty would follow from fidelity. The images, frost-like webs, pearl-bright clusters, were not decorations. They were the bones of reality, revealed by rules. With that confidence, attention turned to the luminous. If Millennium was a grand sketch of scaffolding, the next step was to paint the breadth and heat of galaxies themselves. In 2014, an international team released Illustris, a simulation that did not stop at dark matter. It gave gas a voice, allowed stars to ignite and age, and let black holes feed and answer back. The box was smaller, about 350 million light-years on a side, but the detail deepened. More than 12 billion resolution elements, particles, and fluid cells carried mass, velocity, temperature, and traces of chemistry. As time advanced, these properties changed according to equations for gravity, hydrodynamics, radiation, and the feedback that stars and black holes send to their neighborhoods. At the heart sat a moving mesh method called a repo. Instead of carving space into a rigid grid, it let the mesh drift with the flow, refining where structures sharpened and relaxing where space was quiet. In practice, it meant the code could keep its attention where the stories were: spiral arms folding in, shock fronts rolling out, clouds cooling, condensing, and lighting. Feedback, the difficult art, took its place as well. When massive stars died, they heated and stirred the gas around them, slowing new births. At galactic centers, supermassive black holes released energy that could warm halos, drive winds, and sometimes hush star formation completely. These processes act on scales too small to resolve, so the team used subgrid rules, honest stand-ins tuned against observation. The result felt startlingly lifelike. Disks unfurled with a grace we know from photographs. Massive ellipticals bore the marks of ancient collisions. Tidal streams arced and faded. Comparisons with surveys showed a pleasing alignment. The mix of galaxy masses and colors, the way systems clustered, the patterns of star formation across time. Not perfect. Some galaxies came out too compact, some too rich in stars, but close enough to teach. And the pictures, rendered from the data, were more than beautiful. They were explanatory. A color wash could show temperature, a contour could trace density, and suddenly, the eye could see how energy spread and where structure took root. Success invites the next try. The team pressed forward with Illustris TNG, the next generation, a suite of simulations that expanded volume and deepened physics. The largest, often called TNG 300, spanned a space nearly an order of magnitude larger than Illustris's high-resolution box. while improved models tracked magnetic fields, stellar winds, black hole feedback, and the slow enrichment of gas with heavy elements like carbon, oxygen, and iron. In these runs, the diversity of galaxies felt truer: delicate spirals in quiet neighborhoods, puffed lenticulars along filaments, giants settled into elliptical calm after long, bright youths. The energy released by black holes proved central for producing the massive, dormant galaxies we see today. Their star-making days ended by a long, gentle heat. From the outside, these projects look like art, and in a way they are patient composition, deliberate choices, a devotion to form. But underneath the color is a working hypothesis, checked and rechecked. Change the efficiency of turning gas into stars. The population shifts. Turn up the black hole feedback. Galaxies quench earlier. Halos heat more. Winds carry metals farther into intergalactic space. Nudge the recipe for turbulence or cooling. Arms grow looser or tighter. Disks thicken or thin. Each adjustment is a question posed to the sky, and the comparison to data is the soft answer that comes back. There is quiet philosophy living in these rooms of code. If a simulated universe can resemble the real one so closely, what does that say about understanding? Not that we have solved the whole, only that the rules we hold are strong in the places we've used them. The Millennium Run succeeded because the starting ripples and the nature of dark matter were set by the best evidence we had. Illustris and TNG succeed because their feedback rules are anchored to observation. Where they drift, they point the way to what is missing: the fine play of magnetic fields, the exact temper of early stars, the truth about dark matter's nature, still shy and unlit. The practical gifts are many. Mock surveys let observers test their methods, how a selection bias might tilt a result, how dust or distance might hide a class of galaxies, how lensing can be modeled against a true mass map. The same data sets train new instruments to recognize features in the noise. The same run can be rewound, a parameter nudged, the story replayed. Nature refuses retakes. The machine allows them, gently. Under the numbers, the language stays simple. Gravity gathers, gas flows, light carries energy away, feedback answers in return. A handful of constants anchor the arithmetic. Time is sliced thin, then thinner, until the steps are small enough that the world does not stumble. Where detail is beyond reach, subgrid rules take the place of full physics, but only after the sky has had its say about what the averages must be. If the Millennium simulation opened a window onto the universe's bones, Illustris, and then TNG eased up the dimmer and sent color back through the frame. Dark matter filaments read like neural tracks. Galaxies blinked along them as if signals were passing through a patient mind. Warm winds of gas carried the memory of past outbursts. Those images walked out of journals and into classrooms and studios where people who care about form as fiercely as fact found something to hold that matters. Inspiration keeps the work humane and unhurried, the way steady hands keep a quilt even and kind. It still began with a simple bravery: leave the equations running long enough to grow a world, a box roomy enough to cradle a slice of forever, 10 billion markers for the unseen, a moving mesh to follow how gas breathes and curls, rules for stars and for rest, for heat and for letting go. Then the listening: compare, revise, compare again, wait while the code tells a story the sky is willing to recognize. The fit is never perfect, should never be. In the difference tomorrow finds a place to start. So the digital cosmos turns by careful increments. In one run, a cluster sends a shock through its heart like a slow pulse. In another, a spiral leans into its arm and gathers bright company along the rim. Far off, a void deepens and keeps its counsel. The room stays quiet through all of it. What changes is us. Patience grows a shape from numbers, and in that glow we see not only what is out there, but how our understanding learned to walk toward it. Let beauty arrive as a side effect, truth's afterglow when given time. At first glance, a galaxy simulation is nothing much to look at, only a river of values, positions and speeds, masses and temperatures, a soft broth crossing a virtual room. But inside those decimals, something begins to lean forward. With patient tools and enough hours, the stream thickens into a figure we know, a disk that breathes, a halo that gathers, a galaxy curling back through itself, the way a tide returns to a quiet harbor. The change from numbers to meaning begins with motion, every particle standing in for dark matter, gas, or the bundled light of many stars owns a position and a speed. These are not dots on a frozen page. They obey the same gentle laws that steer the sky. At each small step, perhaps a million years of cosmic time, the machine asks how gravity, pressure, and radiation should nudge them. It answers softly, frame by frame, and the choreography accumulates until a pattern holds. Gravity arrives first, unhurried and tireless. Long before a single star turns on, unevenness in the young universe begins to grow. Small lumps become larger ones pull in more mass. This quiet amplification, gravitational instability, raises halos of dark matter, the invisible shells that will cradle whatever glows. Dark matter itself never shines, but without its patient scaffolding, the luminous would drift like fog, pretty and formless, soon lost. As halos deepen, ordinary gas, hydrogen, and helium left from the beginning falls inward, warms, and starts to swirl. Here the dance gains texture. Gas is treated as a fluid, so the code tracks not only where it goes, but how it moves. Compression and cooling, shocks that ring like distant thunder, eddies folded into eddies. Some patches grow dense and cold enough to invite stars. The model does not follow every molecule and magnetic whisper. That would be a different lifetime. Instead, it keeps a recipe, a star formation rule of thumb. When a region crosses gentle thresholds, high density, low temperature, enough mass gathered, some of its gas is converted into star particles. A star particle is not a single sun. It is a chorus, often millions or even hundreds of millions of stars represented as one note. Each carries an age, a mass, a measure of metallicity, the heavy elements inherited from older generations. Time moves. Some fade, some explode as supernovae, releasing heat and newly forged elements into the surrounding gas. That feedback stirs the pot, slows some births, hastens others, and sketches the rough weather of a forming galaxy. The raw output is still just numbers until we teach the eye to listen. Mass becomes brightness, temperature becomes color, density becomes contrast. Spiral arms appear not because an artist painted them, but because angular momentum and gravity fold gas into streams that wrap around a center. Ellipticals puff out of old collisions. Tidal bridges stretch between neighbors, like quiet fireworks seen from far away. These images are lovely because they are honest. Structure shown exactly where the rules place it. Pictures carry meaning. Researchers read them for the balance of old and young stars, for for the speeds of rotating disks, for the paths of gas that is driven inward or blown free. They set the renderings beside the works of Hubble and James Webb and ask simple questions. Are the colors plausible? The rotations steady? The proportions of dust and starlight believable? When the answer is yes, confidence deepens. When the answer is no, the code returns to the bench and a knob is tuned with a steadier hand. A quiet surprise is how intuitive these scenes can feel. You do not need training to recognize when a disk looks too thick or an arm too stiff. Our minds are built for patterns, and galaxies, even across unimaginable scales, obey forms we somehow know. Watching them bloom out of arithmetic invites the same calm satisfaction as seeing a flower open in slow time, unexpected and yet inevitable. And the best moments are the unplanned ones. Simulations produce features no one requested: a stream of stars peeled from a small companion, a filament of gas twisted into a luminous arc, a void clean as a held breath. These are not decorations. They are emergent facts. They arrive because the rules were allowed to run without supervision, because gravity and flow were given room to speak to each other. When such structures match the sky, delight gives way to trust. When they do not, curiosity sharpens. Perhaps the feedback from young stars was too gentle. Perhaps black holes need a stronger voice. Perhaps the gas should cool more slowly. To coax numbers into sight, you need more than equations. Visualization tools YT, OpenSpace, and the custom renderers built like small observatories translate data into images and journeys. They set color maps, mimic lighting, and let you drift through layers of structure. A slow comet gliding past virtual shores of starlight. 1 billion years passes in seconds. A galaxy collapses, spins up, lights, and brushes shoulders with a neighbor. What nature refuses to show in a single lifetime, the machine reveals as a sequence of patient frames. Even tuned against observation, simulations reach beyond the known. A run might predict a kind of merger not yet seen, or a halo of thin, warm gas that tomorrow's instruments could catch. In that role, they do more than reflect. They propose, they sketch the unseen margin where the next generation of telescopes may find their prize. Under the color and motion lies a simple comfort. The universe keeps rules. Learn a few well enough, and you can build small truths that stand on their own, not with atoms, but with algorithms, not with a glass mirror, but with time loops and lines of code. Out of that digital air, galaxies gather. They shimmer, they trade stars and simmer with winds. The feeling that rises is not that we fooled the eye, it is that we listened long enough to let the rules write themselves. In that sense, the pixels are not pretending to be galaxies. They are galaxies of another kind, born of gravity, fluid motion, and computational patience. Now try to paint a landscape whose main feature is invisible. Trees bend, rivers turn, shadows stretch, and none of it makes sense until you admit a mountain no one can see. That is dark matter. No telescope images it, no lab has held a particle up to the light, and yet its gravity shapes almost everything. The reach of halos, the weaving of filaments, the steadfast spin of disks that would fly apart without it. The work begins with honesty. We do not yet know what dark matter is. It is not ordinary atoms. It ignores light. It does not clump into stars or dust. But it answers gravity, and gravity is a language we speak. Decades ago, the rotation of galaxies told us something was missing. Stars at the edge were moving too quickly to be bound by the visible alone. It was like watching a carousel whirl with invisible riders that nonetheless held the horses to their poles. The simplest explanation was extra mass we could not see. In code, gravity is the great equalizer. Give a thing mass and it will tug and be tugged. So simulations seed dark matter as particles with weight and let the collective pull decide the shape of the world. The initial pattern comes from the early universe, tiny ripples mapped in the cosmic microwave background, a few 100,000 years after the beginning. Place dark matter according to those ripples. Press start and wait. Each particle really stands for a large clump, often the mass of several million suns of invisible matter. It does not cool or radiate. It drifts, falls, and gathers, driven only by mutual attraction. Over billions of years, halos rise, swallow neighbors, and grow. Inside them, ordinary gas can settle and build galaxies. Between them, space stays spare. The result is a scaffold, the cosmic web drawn from invisible thread. Filaments span great distances and meet at nodes where halos thicken into the crossroads we call clusters. Vast voids open between strands. We see the same geometry in surveys and in lensing maps, a deep rhyme between prediction and sky. What startles, still, is how far you can go with dark matter alone. Even with no gas, no stars, no black holes, a simulation can reproduce the broad structure of the universe, the placement of clusters, the scale of voids, the texture of the web. That is how dominant the unseen is. To understand the details of galaxies, you must add ordinary matter and its more complicated habits, cooling and shocks, radiation and chemistry. Then the two components drift apart in personality. Gas forms disks, lights briefly, and sheds winds. Dark matter, unmoved by light and heat, continues its patient collapse, the silent conductor, keeping time. Every model faces a choice about character. The leading picture is called cold, dark matter. Cold, meaning slow compared to light, slow enough to clump on fine scales. Competing ideas, like warm, dark matter, smooth the small features by giving the particles a little more speed. These differences leave signatures. Cold dark matter predicts abundant tiny galaxies and thin, crisp filaments. Warm dark matter softens the map, comparing simulations with surveys, counting dwarf companions, weighing halos with lensing. Tracing streams around the Milky Way lets astronomers test which melody the universe prefers. The debates are careful, sometimes spirited, because the smallest notes can change the whole song. Look closely at a simulated halo, and you will see structure within structure. A dense heart, a thinning cloak, streams from past mergers still winding through the dark. These cocoons are not solid. They are memories, overlapping histories of everything the halo has eaten. The biggest halos host clusters of galaxies. Near their centers sit supermassive black holes, fellow mysteries that seem to thrive wherever dark matter builds the deepest wells. The moment the two tapes braid dark scaffolding and luminous habit, the scene gains breath. Halos offer shelter, and galaxies take it. Nodes knot, and clusters light up, while the wide lanes between filaments stay spare and quiet. It doesn't match the sky, stitch for stitch, and it shouldn't. The closeness is what guides. When a disk forms too eagerly, we learn to cool the recipe for stars. When a cluster grows sullen, we stiffen the wind from a central black hole. If the web looks too smooth or too grainy, We retune the first ripples that seeded it. The misses are arrows, not wounds. And still the main actor refuses a bow. We have not caught a dark matter particle in the lab. Names gather around the absence. Wimp axion. Something stranger, but the evidence keeps its patience. In models, though, the behavior is stubbornly consistent, almost like temperament. Remove it, and spirals lose their poise. Lensing goes slack. Clusters come unstitched. Leave it, and the melody holds. Listening for it is like listening for a silent instrument. You never hear it alone, only the way the ensemble collapses when it's gone. There's comfort in that odd arrangement. What we know least steadies most. Simulations teach us to honor footprints when the walker makes no sound. We follow the pattern through rotation curves that refuse to fall, through the arcs of bent light, through clusters that keep their shape in rooms of near nothing. On digital skies, the dark returns the only way it ever does in gravity's grammar, lightless and exact, guiding the visible from the wings while the numbers hum a distant, even chord. Every run starts with a small, deliberate kindness. Decide what to carry across the threshold and what to set down, not for lack of curiosity, but because no room, not even a hall of supercomputers, can host every eddy at once. That isn't failure, it's the craft. A simulation isn't a mirror, it's a map. Good maps prune. They leave enough forest to show where shade lives, enough river to follow a valley, enough mountain to understand the climb. Cosmology works the same way. We trace the rise of galaxies and the knitting of structure, the long drift of dark matter and gas across deep time, but we do it with declared shortcuts and careful approximations, each named, each owned, so that paths stay visible and the journey remains possible. Resolution is the first gentle gatekeeper. A photograph has pixels. A universe in code has resolution elements, particles, cells, points on a grid. More elements mean finer texture, but there is always a limit. No machine can track every atom, not even every star. So we bundle. A single star particle might stand for a whole cluster. A single gas cell might span light years. The furious small weather of reality, turbulent swirls, tiny shocks. A supernova's ragged edges is softened into an average. Where the microscope would show chaos, the model keeps a simpler melody. Small-scale processes do not vanish. They arrive through recipes called subgrid models. Star formation is not followed molecule by molecule. Instead, when gas becomes dense enough, cool enough, and heavy enough, a rule says, part of you becomes stars now. It's a promise written in code, tuned to match the galaxies we actually see. Make the threshold too generous, and the sky in the box fills too quickly. Make it too strict, and everything stays dim. Then comes feedback, the way stars and black holes return energy to their neighborhoods. A real supernova blasts out in clumps and knots. An active galactic nucleus can push jets across thousands of light years. In code, these tempests become energy added to nearby gas cells, gentle where nature is jagged, uniform where nature is patchy. Calibrating that push is a delicate art. Too weak and gas pools quietly, birthing stars without pause. Too strong and the wind sweeps a galaxy nearly clean. Magnetic fields thread the scene like invisible embroidery. They guide charged particles, lend shape to flows, and may set the rhythm of star birth in ways we do not fully grasp. Some simulations accept the cost and include magnetohydrodynamics. Many soften it or skip it to keep the clock from stalling. Cosmic rays, fast. Small travelers with outsized influence often sit in the same waiting room. They ferry momentum, heat gas from far away, and may help regulate galactic winds. Including them adds complexity. Leaving them out adds a question mark. The choice is noted in the margin, either way. Even gravity, the patient backbone of the story, is sometimes simplified. Most large runs lean on Newton's steady law, perfectly fine for most of the cosmic stage. General relativity, the full curve and grace of space-time, matters near black holes and in the bright flash of the early universe. Bringing it in wholesale is expensive. So many projects reserve it for focused scenes. The honesty is simple, close enough, here, deeper, later, when the scene demands it. Chemistry hums beneath all of this. Real clouds are not only hydrogen and helium. Stars forge heavier elements, and supernovae scatter them like seeds. Those metals help gas cool, color the light, and tilt the odds toward or against star formation. Some simulations track detailed enrichment. Others carry a single metallicity value, a shorthand that saves time but smooths away intricate patterns a chemist's heart would love. Radiation is another whispering power. Light warms gas, strips electrons from atoms, pushes dust. Following every ray through every cloud is a labyrinth of math. Many models take a simpler path, a uniform background here, an approximate local source there. On large scales, it sings the right tune, close to a young star cluster, carving a bubble out of dense gas. Nuance matters more than averages can give. Dark matter and dark energy keep their familiar mysteries. We let dark matter tug without shining, cold, and mostly collisionless, because that is what the sky suggests. If it turns out to be warm or fuzzy or layered, the map must be redrawn. Dark energy is often allowed to be a simple, constant pressure that speeds expansion. If it evolves or converses with other fields, most boxes will not notice because they were not built to listen for that voice. None of this is failure. It's a ledger, assumptions, written in the corner so we can check them later. These exclusions do add up. Sometimes a mismatch with observation is nature surprising us. Sometimes it is a recipe too plain. The quiet strength of simulations is how they make such questions testable. Turn on magnetic fields and watch spiral arms change their posture. Add cosmic rays and see a galaxy's core grow gentler. Give black holes a stronger voice and count how many massive galaxies fall silent. Each run becomes a hypothesis spoken aloud, an idea in the shape of a world ready to be compared with the sky. There is a tender humanity in this work. The gaps reflect our limits, what we cannot yet compute, what we do not yet know, what we must soften so the story will fit on the page. But the gaps also reveal our creativity, the way we distill, adjust, and test, turning an impossible tangle into something a mind can hold. When you see a luminous spiral from a simulation, you are looking at two things at once: a model of what we've learned and a lantern for what we haven't. Imagine a jigsaw puzzle that covers all of time, from the warm afterglow of the beginning to the cool swirl of tonight's galaxies. You can study a single piece in exquisite detail, or you can back away until the whole picture shows, but not both at once. That is resolution. In code, resolution is the smallest feature you can follow. How thinly you slice space, how finely you portion time, how delicately you parcel mass. Higher resolution means richer texture and heavier cost. Spatially, the universe in a box is either a grid of cells or a sea of particles. Make the cells smaller or the particles lighter, and you capture smaller structures. Do it across a large volume, and the cost multiplies until even the largest machines fall quiet. A run like the great galaxy-forming boxes may use tens of billions of elements to cover hundreds of millions of light years. It's astonishing, and still, each simulated galaxy may be built from only thousands of star particles and gas cells. The real thing holds hundreds of billions of stars. The model sees a soft smear, a faithful average of many details, rather than the details themselves. That is not a bug. It is a choice made on purpose. These grand volumes answer grand questions. How do galaxies cluster? How does dark matter sculpt the web? How does feedback regulate the rise and hush of stars across the age of the universe? For such questions, statistics matter more than eyelashes. The broad pattern reveals more than any single flourish. To watch a single galaxy breathe in finer detail, the volume shrinks and the resolution climbs. Then the model can follow cold clouds gathering, shock fronts rolling, jets from a central black hole threading the halo. The trade is immediate. The big picture fades. You cannot cradle a universe and a molecular cloud in the same palm without cutting corners that would make both blurry. Temporal resolution brings the same balance to time. Quiet regions can take long steps. Busy regions need shorter ones. Many codes use adaptive clocks, fast ticks near a star-bursting heart, slow beats across a tranquil void. Without that care, a simulation can glide past its most important moments. A collapse that should have sparked a cluster, a merger whose brief violence reshaped a disk. Feedback is especially sensitive to resolution. In a coarse model, a supernova might warm a large gas cell and simply drift back to calm. At higher resolution, the same explosion can drive nested shock waves, trigger new births at the shell, and carve a chimney out of the disk. Two runs, same physics on paper, different stories on the screen. This is why convergence tests matter. Repeat the scene at several resolutions. If the melody stays the same, the theme is strong. If it changes wildly, the result was made of sand. Tiny galaxies carry their own lessons. Dwarfs and satellites are easy to erase at low resolution. They blur into the background and vanish. Yet they carry clues to dark matter's character and to the history of star formation in harsh neighborhoods. To save them, techniques stretch. A popular one is the zoom-in. Run a large, low-resolution universe to find a place of interest. Then, resimulate that patch at fine detail, while the larger world keeps its broad influence around it. It's like studying a city block while still feeling the weather of the continent. Zoom-ins, for all their grace, are tailored suits. They fit one region beautifully but do not clothe a whole population at once. When thousands of galaxies must be seen together, other tricks help. Machine learning surrogates learn from expensive, high-resolution runs and then paint in the missing texture on cheaper, coarse ones. It doesn't replace physics, but it extends reach, another way of keeping the spirit of detail without paying the full price every time. Beneath the craft sits a steady truth. You can't hold the whole forest and the single leaf in the same palm. Every model chooses its balance, breadth against depth, panorama against close-up, and that choice isn't whim. It follows the question. If the puzzle lives on scales where filaments braid across billions of light years, a wide, slightly softened gaze is wisdom. If the mystery lives in a black hole's hush or a cloud's decision to bead into stars, we trade horizon for intimacy and let the distance blur. Even so, the compromises keep surprising us. Coarse pixels still outline highways through the dark. Smoothed galaxies still collide, heal, and settle into fresh shapes. We watch dark matter set the stage. We hear feedback score crescendos and rests. We see the faint swell into brightness and drift back toward quiet. Resolution isn't only a limit of hardware, it's a way of paying attention. What is tonight's work, a pattern stretched from cluster to cluster, or the delicate weather inside one bright island? Either choice can be right. Both insist on care. The aim isn't to see everything, it's to see enough. Enough to let noise relax into form. Enough to bring tomorrow's question into focus. Enough to glimpse scaffolding under the stars and softness inside a storm. Now and then, even through blur, the scene steals breath. A spiral arm stepping out of haze, a shock front moving like a low drum, a shy dwarf walking into view. In those moments, the trade-off feels less like a fence and more like a way of listening, a gentle narrowing so meaning can arrive. Calibration lives close to that same patience. It's a kind of baking in the dark. Some ingredients are learned by heart, gravity, dark matter, gas. Others by touch. How easily should stars appear? How fierce the breath of a supernova? How far does a black hole's heat wander before it cools into silence? Mix, wait, taste the sky against the code. If galaxies bloom too quickly, if voids come too timid, ease a dial, strengthen another, and try again. It is science, honest, careful, repeatable, and also the calm intuition of guided art. In a world without limits, the code would need no tuning. You'd set down the laws and watch a faithful universe walk out, complete and sure of itself. Our world is kinder and messier. The cosmos is richer than our calculators and finer grained than our grids. So models carry parameters: how efficient star formation runs, how much energy a supernova lends to its neighbors, how strongly a black hole feeds back, how gas cools, how radiation brushes dust. They aren't arbitrary. Each is measured against the sky and kept only if it earns its place. The dials exist because nature's smallest rooms are still smaller than our largest machines, and until we can enter them outright, we tune by ear to keep the melody true. Think of star formation efficiency as the softness of the oven. Real stars appear from cold, dense clouds, and most gas never crosses the threshold. Simulations cannot model every molecule and magnetic whisper, so they keep a rule. When gas becomes dense, cool, and heavy enough, a fraction turns into stars. Too generous, and the model becomes a factory of blue giants. Too stingy, and disks flicker weakly, unable to match the glow of real surveys. The right value appears when many independent measures align: galaxy brightness, rotation speeds, colors across time. Feedback asks for the same careful ear. A supernova is not a tidy flare. It is a jagged wave rushing through a messy neighborhood. Codes approximate that fury by depositing energy and momentum into nearby cells. Too little, and gas settles back as if nothing happened. Too much, and winds strip a galaxy bare. Somewhere in between, spiral disks hold their shape, bulges grow modestly, and star formation falls into a steady breathing. Black holes require a deeper patience. Feed them too quietly, and massive galaxies stay bright far too long. Feed them too violently, and the lights go out everywhere at once. Observations of quenched ellipticals, of hot halos in clusters, of outflows traced by X-ray and radio anchor. The tune: how often do black holes accrete? Where does their energy land? As heat smoldering through a halo, or as narrow jets threading the dark? Adjust, compare, repeat. When the same set of parameters explains not just one measurement, but many stellar masses, gas fractions, color distributions, cluster temperatures, you begin to trust the melody. Calibration is not cheating. It is tempo. The symphony is already written in the laws. Tuning sets the downbeat, so the players enter together. Still, there is a fair worry. Tune too much, and the model becomes a hall of mirrors. To guard against that, scientists choose one target, say the galaxy stellar mass function, to set their dials, then test against others left untouched: the size of voids, the pattern of clustering, the temperature of intracluster gas, the relation between star formation and halo mass. When those unaided tests pass, confidence settles like warm light. Even then, the work stays humble. A simulation can be convincing for the wrong reason, like a model forest that matches tree counts while secretly believing trunks are ice. That is why failures are cherished. Too many dwarfs? Perhaps feedback from young stars must couple differently to cold gas. Disks too thick? Perhaps turbulence or magnetic support was misjudged. A cluster too cool in its core? Perhaps black hole heating needs a wider reach. Each miss is a signpost, pointing from pretty picture to missing physics. Beneath calibration lies a quieter question. What do we mean by prediction? It is tempting to imagine simulations as crystal balls: feed in laws, press run, and wait for truth. But prediction in cosmology is not tomorrow's umbrella. It's a test of consequence. If these laws and these beginnings are right, do we naturally arrive at webs and clusters and colors like the ones we see? Early runs foretold the cosmic web before surveys stitched it in detail. Models forecast how dark matter halos should bend light, and lensing maps later drew the same shapes on the sky. Those were not tricks. They were glimpses of law unfolding. The strongest predictions are often counterfactuals: warm dark matter versus cold, constant dark energy versus a restless one, black holes that whisper versus those that roar. We cannot tour those universes with telescopes, but we can compute their echoes. If a model produces too few dwarfs or wipes away thin filaments, and the real sky is busy with both, the idea steps aside. If a model yields heavy, sleepy galaxies at times, and places where observers later find them, the idea earns a longer look. Sometimes predictions arrive sideways, through consequence rather than spectacle. Calibrated black hole feedback that quenches big galaxies also heats cluster gas and enriches the intergalactic medium in a specific pattern. If X-ray and absorption line studies see that pattern, a web of support tightens. Slight changes to early density ripples might alter not just the abundance of clusters, but the rhythm of star formation across time. If deep surveys trace that same rhythm, a different thread is tied. Still, a match is not a crown. Convergence is not confirmation. You can tune a galaxy population and miss the physics that truly drives it, just as you can sketch a convincing face without understanding bone and muscle. That is why simulations are best treated as laboratories, not verdicts. Turn off black hole feedback and watch massive galaxies blaze. Halve the star formation efficiency and see disks stay gas-rich and green. Add cosmic rays and watch winds widen and cool. These are controlled experiments the real universe will never run for us. The best work keeps a double ledger. Parameters chosen, data used for tuning, and a list of tests left clean. It also keeps room for surprise. A simulation that reproduces known counts and then quietly predicts a class of faint, metal-rich dwarfs in cluster outskirts gives observers a target. If the dwarfs are found, we learn twice about galaxies and about the good faith of our map. There is philosophy here, but it moves softly. The universe is under no duty to be simple, and yet it keeps allowing our simple rules to draw its outline. When code, tuned with care, produces a disk that rotates at the right speed, shines with the right light, and carries the right mix of young and old, the feeling is not triumph so much as relief. The instrument was tuned. The note rang true, not perfect, never final, but true enough to guide the hand. And then the harder question returns. Are we predicting or staging? Perhaps both. We rehearse with the score we have, and then we ask the orchestra to play the next movement we have never heard. We guide by data, and we let the laws run beyond what the data yet allows. When new telescopes look deeper, finding early, massive clusters, measuring lensing with finer precision, catching winds in the act between galaxies, we learn whether our rehearsal held. Failures remain our companions. A model overheats the circumgalactic medium. Another makes disks too small. A third lets black holes fall asleep too early. Each misstep is a kindness in disguise, a clear instruction to reshape a subgrid rule, to refine the coupling of energy to gas, to reconsider the smoothness of the early fabric. In that sense, simulations always predict one thing with certainty, where our understanding will need to grow next. So the work continues, slow and warm. Calibrate one melody star formation in middling halos and test another quenching in giants. Tune feedback to hush a cluster core and listen for metals drifting into the void. Set the downbeat with today's surveys and ask tomorrow's instruments to answer back. What emerges is not a boast, but a conversation between code and cosmos, between expectation and surprise, between what we ask and what the universe allows. And when a run finally settles, spirals steady, clusters breathing heat, dwarfs shy but present, there is a small human pleasure, not because we forced a likeness, but because the laws we chose spoke clearly enough that the picture drew itself. The chords resonate, the sky answers. Not perfectly, not completely, but with a clarity that lets the mind rest. We have not built the universe. We have tuned a modest instrument to play along with it, and the harmony, however fragile, is real. At a distance, a simulation can look like a tidy blueprint. Laws in, universe out, no wiggle room. Sit with it longer, in a quiet room where the fans hum and the cursor blinks and another pulse emerges. Chance moves under the equations like a second heartbeat, not a flaw, not a loose screw, but part of the instrument itself. Without those small, lawful rollings of the dice, the digital sky would stiffen and the story would lose truth as well as color. We never start from a polished sheet. The infant universe carried faint ripples, recorded in the cosmic microwave background like grain in old film. What we know are their statistics, the power at each scale, how often a fluctuation of a given size should appear, how that power falls off or rises with wavelength. What we don't know is the exact pattern in every corner, so the code builds a field that obeys the statistics and lets randomness decide the specific bumps and hollows. Gravity reads that map and leans toward the slightly denser parts. Knots grow, knots become halos, halos cradle galaxies. Change the initial speckle by a whisper, and the large picture shifts by a shade, familiar yet newly arranged. It's closer to baking than blueprinting. One recipe, many cookies, same flour and heat, different freckles and edges. A simulated galaxy is that kind of cousin plausible, not identical. The rules guide the rhythm, the root belongs to probability. Gas collapses sooner here, later there. A merger arrives mid-song or misses its cue. Feedback from young stars rattles a cloud into new birth or blows it open and leaves quiet behind. Same score, different performance. Even the decision to form stars is written as odds, not orders. When gas becomes cold, dense, and gravitationally bound, the program doesn't snap a switch. It listens for thresholds and then assigns a chance. This tick, a new star particle appears. Next tick, it doesn't. Then two at once. Tanting, in real space, vary wildly. The stand-ins do too. Some dump energy in a rush. Some bleed it slowly. Some spark more stars by compressing shells. Some end a neighborhood's bright season. Black holes add their flicker accretion rates wandering, jets pulsing, orbits lining up just so for a merger once in a long while. Those jitters are not cosmetic. They are the grain of the music. Skeptical minds ask whether a world that throws dice can be trusted. The answer lives in the difference between random and lawless. Coins are random. The bell curve they draw after 1,000 flips is not. Simulations promise population truths, not celebrity portraits. Mass functions, star formation histories, how galaxies cluster, the color mix at a given epoch. These are the claims that matter, and they are statistical. If the digital population matches the sky's population across many measures, we call the model honest. To separate physics from luck, the work repeats with new seeds, dozens of runs, sometimes hundreds. Patterns that survive these reshufflings belong to the underlying rules. Features that wander are labeled weather. Then the conclusions arrive with edges, not a single number, but a range, not certainty, but odds you can write down and compare with data. The real universe is one draw from many possibilities. This ensemble way of thinking is an act of respect. That shift changes how the pictures are read. A luminous spiral on the screen is not meant to be your spiral. It's a sentence in the grammar of gravity and cooling, spoken with a local accent. If only a few runs produce a Milky Way twin that whispers about rarity, if none ever yield a certain bright dwarf, the silence is loud. Perhaps feedback is too strong in small halos. Perhaps the star formation threshold sits a touch high. Perhaps a whole piece of physics waits outside the frame. Surprises are not reserved for beauty shots. They arrive as mismatches, and mismatches are generous. Imagine months of careful tending equations aligned, code quiet, galaxies spinning politely, and the comparison lands with a thud. Disks look too smooth, halos too dim, colors too blue or not blue enough. That is not a stop sign. It's a signpost. Simulations are instruments built from good laws and necessary approximations. When they fail, They point straight to the places where understanding can grow. The missing satellite story carries that lesson in plain language. Early models predicted that a big galaxy like ours should wear a shawl of tiny companions, each a spark in its own small, dark halo. Telescopes found dozens, not hundreds. Part of the gap was observational. Faint things hide. Deeper surveys uncovered more dim companions and narrowed the space between prediction and sky. The rest lived in the physics of little systems, in shallow wells, newborn stars, and their radiation can push gas back into space before it ever cools again. The dark halos remain. The lights never turn on. Tuning the way feedback couples to low-mass gas pulled the models toward the data without changing the larger song. Another riddle wore the name cusp versus core. Dark matter only typically grow steep, dense centers. Observations of dwarfs, though, often hinted at flat, gentle cores. Two families of ideas met in that gap. One asked whether dark matter might interact with itself enough to soften the center. The other asked whether repeated cycles of starburst and blowout could push matter outward and relax the slope. Add those breath-in, blast-out rhythms to the code, and the central profiles grow kinder. The point is not that one patch fixed everything. The point is that the mismatch told us exactly where to listen. Then there was too big to fail. Some subhalos around the Milky Way looked massive enough on paper that they should have hosted bright satellites, and yet the sky stayed quiet. Perhaps the Milky Way's overall mass was misestimated. Perhaps the efficiency of star formation in those particular wells was overconfident in our recipes. Perhaps a stranger twist in the rules waits. Questions like that don't bruise the field. They sharpen it. Measurements tighten. Algorithms refine. Observers design new hunts. And the line between model and world grows thinner. Zooming in exposes other edges. Large-scale structure, the web, the clusters, the slow strengthening of contrast is gravity writing in a bold hand. Inside a galaxy, the handwriting turns small and quick. Turbulence tangles, cooling races and stalls. Magnetic fields thread the flows. Cosmic rays carry heat and momentum into delicate places. No large cosmological box can resolve it all. So subgrid physics enters as honest shorthand for what the pixel cannot see. Shorthand has blind spots. Disk thickness, the shape of bulges, how neutral hydrogen lies across a disk. These are tests that catch lazy approximations and send the coders back to the bench. Observations bring their own weather. Dust hides. Instruments saturate. Distances stretch. Light and blur, meaning turning thin light into thick truth is a brave act of inference. Here, simulations offer wind tunnels for interpretation. If deep fields suggest star formation sprinted earlier than expected, the code can ask whether ordinary physics, under the right pressures, naturally runs that fast, or whether a deeper change is required. If weak lensing maps hint at substructure a certain way, a suite of runs can show which dark matter picture reproduces that texture without overfitting the rest. None of this sets pixels and photons in opposition. They move as partners. Measurements lead the calibration. Models keep time and learn the steps. Then the roles trade. A run proposes a flourish, a rare class of quiescent dwarfs in cluster outskirts, say, and the telescopes go looking. When the rhythm slips, we do not declare a winner. We adjust the tempo, or admit that the tune has a verse we haven't learned yet. Successes, too, deserve their quiet nod. Filaments stretching across billions of light years lived first in code before surveys stitched them from galaxy positions. The gently ringing scale of baryon acoustic oscillations, broad cluster architectures, certain correlations among galactic colors and masses. Many arrived as previews on screens, and only later as confirmations on the sky. Confidence grows there, not as swagger, but as warmth. Simple rules, tuned with care, walking out into the dark and recognizing the streets. Underneath runs a softer, more philosophical question. Are these models predicting or staging? The honest answer is both. We rehearse with the parts we've heard, and then keep playing into the silence. We tune to the data we own, and let the laws run past the frontier of observation. New instruments open, and the rehearsal is graded. Massive clusters found earlier than we guessed. Perhaps the initial ripples were a touch different than assumed, or black hole feedback shaped gas in a way we missed. Lensing measured to finer lines that favor one dark matter temperament over another. A few dials move, and the orchestra's balance shifts. The music deepens. Randomness holds all of this in balance. It reminds us that the universe is an improvisation with rules, not a script with stage directions. That is why ensembles matter. That is why uncertainties belong beside every figure and caption. It's also why the cleanest gift a model offers may be the place where it breaks. Overheated circumgalactic gas points to a feedback coupling that spills energy in the wrong way. Too many dwarfs light up, and the handshake between young stars and cold clouds needs a new grip. Massive galaxies refuse to quench. The central black holes are still whispering when they should be singing. The work goes on calmly. Seeds are chosen with care. Laws are stated with respect. Dials are placed not to flatter expectations, but to honor what the sky already said. Dice are rolled fairly. Universes bloom and fade on screens while real photons cross real darkness toward real mirrors. When a run settles into itself, spirals steady, clusters warm, shy dwarfs present, you feel a small, human relief. Not triumph. Relief that the few rules we trusted sang together long enough for a picture to draw itself. What are we offered by this practice? Not certainty, something gentler, a way to make chance visible and law audible, a way to feel the harmony that hides inside the noise. A single frame of filament glowing along dark matter bones. A supernova's pulse traveling like weather through a nebula doesn't read as pretense when it grows from equations that have been honest about their limits. It reads as physics with a lilt. The universe would carry on without our models. Our models exist to listen. When code and cosmos hum in tune, even briefly, the chord is clear enough to guide a hand, soft enough to invite a better question, and honest enough to leave room for the next surprise. Before galaxies took their first slow breaths, before stars learned to burn, before atoms finished assembling their tiny planets of protons and electrons, the early universe carried wrinkles, fleeting fluctuations in a field that filled everything. Not waves on top of space, but shivers within space-time itself. Those quantum jitters, smaller than anything a human mind can picture, became the seeds of the largest things we know. Their echo hasn't faded. It rides in the faint microwave glow stretched across the sky and hums inside the code we use to build digital universes. A perfectly smooth beginning would have been quiet to the point of boredom. Instead, space inflated an abrupt, runaway stretch in the universe's first moments. Quantum flickers normally confined to subatomic neighborhoods were tugged to astronomical scale and then held in place, like air pockets trapped in rising bread. Gravity noticed. Where matter ran a touch richer, its pull grew slightly stronger. Where matter thinned, the pull eased. Over time, those gentle tilts deepened. A delicate swell turned into a gathering point. A shallow well became a basin, and matter flowed toward the basins in patient streams. We can still read the pattern. The cosmic microwave background, the universe as a baby, about 380,000 years old, carries a map of tiny temperature differences. One patch, a few millionths of a degree, warmer than the next. Behind that small warmth, a hair more density. Those small differences are not decoration. They are the opening notes of structure. When scientists initialize a cosmological simulation, they recreate a statistically faithful version of that early map. Not the exact arrangement that created our particular sky, but a field with the same power spectrum, the same rules for how big ripples should be and how often they should occur across scales. The computer lays down a three-dimensional lattice of these slight over and under densities. Gravity takes the baton. Dense patches pulled together into threads and knots. The threads weave the cosmic web, and the gaps widen into voids where few galaxies will ever live. Even with only dark matter, no light, no gas, this choreography draws something hauntingly familiar. Filaments arc like rivers seen from orbit. Nodes grow into clusters and superclusters. Between them, dark hollows yawn. The Millennium Simulation, run 2 decades ago with over 10 billion particles, showed how far you can go with gravity alone. A universe of scaffolding built from those first quantum hints. It's a staggering thought that something once smaller than a proton's width could guide structures spanning billions of light years. The laws supply the rules. Probability picks the layout. Ordinary matter complicates the story in all the right ways. Baryons, the atoms that glow, collide, and cool, do more than fall. They crash into themselves. They heat up and radiate. They thread magnetic fields and carry charge. They form stars that later explode. They feed black holes that send jets and heat back into their surroundings. If dark matter sketches the bones, baryons add muscle and weather. We include them because light is how we meet the universe, and without light, a comparison is only half a conversation. There's a pivotal chapter early on, reionization. The first generations of stars and galaxies lit their neighborhoods with hard, ultraviolet radiation, carving bubbles in the fog of neutral hydrogen. Those bubbles grew, met, and overlapped until most of intergalactic space turned transparent. Simulating this era means letting light and matter talk to each other, tracking how ionized regions grow around sources, how their edges move, how they change the way light travels. It is messy, and we are still refining the grammar. The reward is sharp. Signals from this epoch, alongside the microwave background, offer some of our cleanest checkpoints. When a model respects the statistics of the CMB and then naturally grows galaxies with the observed rhythms, confidence gathers. Confidence isn't complacency. Early galaxy runs formed far too many stars, too quickly. Disks grew too compact and too bright. The cure arrived as feedback, and feedback became central. Imagine a quiet disk of gas spiraling within a halo of dark matter. Stars begin to form like slow rain. Then the young ones shout, radiation and winds press outward. Massive stars die as supernovae and shove hot bubbles through the disk. Gas is heated, lifted, and sometimes thrown out altogether. The pace of star birth slows, metals spread into the interstellar medium, and the disk learns to breathe, inhale, exhale, rest. Numerically, that breath is hard to capture. Supernovae act over light-year scales. Cosmological boxes span millions. Subgrid physics, steps in rules that represent small processes without resolving every detail. Energy is injected into nearby gas elements. Sometimes momentum is added. Sometimes the gas is allowed to cool only after a delay so the blast can do its work. Too gentle, and the galaxy ignores the push. Too strong, and it blows itself thin. Somewhere in the middle, rotation curves look right, star formation histories settle into plausible rhythms, and the galaxy's size and surface brightness keep faith with surveys. Black holes add a deeper drumbeat. The supermassive kind, our Milky Way's central object, is modest next to the truly hungry, can sit quiet for eons. When gas finds its way inward, the feeding can turn violent. Quasars blaze, jets lance into the halo, X-rays and heat leak into the circumgalactic medium. This AGN feedback changes galactic fates, especially for the largest systems. Without it, massive galaxies stay blue and busy for far too long, piling on fresh stars. With it, gas in their neighborhoods warms and stays warm. Star formation dwindles and populations age. The result is a sky that carries both youthful disks and dignified ellipticals in the right balance. Simulating AGN feedback stretches our tools. Relativistic jets, tangled magnetism, and radiation pressure deserve more precision than a large box can afford. We compromise again, anchoring the approximations to what telescopes repeatedly show. Hot halos around big galaxies, outflows in clusters, giants gone red and quiet. Feedback doesn't only shape individual galaxies, it writes across environments. In clusters crowded with hundreds or thousands of members, the gas between galaxies, the intra-cluster medium, glows in X-rays. Left to cool freely, it would rain into the central galaxy and light a starburst. Instead, black holes at the core inject energy that keeps the gas aloft. Observations see bubbles, ripples, and gentle heating stretching over hundreds of thousands of light years. Models that build in this cycle land near the truth. Fewer stars in cluster centers, temperatures that match, metallicities that make sense. Those cycles bring chaos that isn't carelessness. Outflows carve bubbles that rise, collapse, and feed new falls. Material thrown into the halo returns in graceful fountains. Metals drift from their birthplaces and seed the next generation. Diversity follows naturally. Dwarfs can lose their gas after a handful of blasts, while deeper wells hold on through dozens. Histories diverge. Some disks live quiet lives of steady accretion. Others are rearranged by mergers and storms. The catalog of outcomes in simulations starts looking like the catalog in the sky. To study that variety up close, the field learned to zoom. A large run first sets the wide context. Within it, an interesting halo is chosen. The initial conditions are rebuilt with especially fine resolution in that patch, while the rest of the volume keeps coarser detail. The Fire Project feedback in realistic environments became a touchstone here. In those galaxies, gas breaks into clumpy, cold clouds. Star clusters ignite and blow shells. Turbulence curls under shock fronts. Outflows punch into the halo and sometimes fall back. The galaxy stops being a statistical smear and starts behaving like a place. That intimacy grants leverage. Adjust the efficiency of star formation and watch a spiral brighten or fade. Change how strongly supernova momentum couples to cold gas and see whether a disk stays thin or puffs up. Let cosmic rays carry heat outward and winds become cooler and wider. Add magnetic fields and dense clouds hold together a little longer against collapse. These experiments aren't the final word. They are careful questions asked in a space where the answers can be measured. Precision comes with cost. Weeks to months of supercomputer time for a single galaxy. Reruns when a parameter proves unwise or a crash interrupts a billion-year story. And selection bias lurks. Pick only Milky Way lookalikes, and you'll miss the lessons of ellipticals, irregulars, and ultra-diffuse ghosts. Teams build suites across mass and environment to compensate, though each new member demands more time and patience. Context thins, too. A zoom remembers its parent volume, but only in broad strokes. The surrounding filaments are present at low resolution, not with the same fidelity a giant box would grant. It's like studying a fish in a detailed tank while the ocean is only sketched on the walls. Initial conditions matter in these close-ups as much as they did at the beginning of time. Slight differences in early density or angular momentum can blossom into different fates billions of years later. Two plausible histories diverging from nearly identical starts. That sensitivity isn't an error. It's a property of nonlinear systems. It does demand care in interpretation. We talk in populations and ranges, not single destinies. Beneath all of this, randomness remains a partner. Star formation in the code is probabilistic. Feedback timing and coupling carry chance. Mergers happen when orbits cross in the right way at the right hour. That uncertainty doesn't make the work sloppy. It forces the right promises, not exact portraits, but reliable patterns. To be sure the patterns aren't accidents. Ensembles are run many seeds, many repeats. If a result survives seed changes and modest model variations, it starts to look like a law spoken through noise. The early stages of structure formation are especially generous for comparisons. The CMB gives a precise canvas. Large-scale galaxy surveys sketch the web. Weak lensing maps weigh the invisible scaffolding. Lyman alpha forests trace gas along sightlines to distant quasars. A model that respects the CMB's statistics grows the right web, bends light as observed, and produces the right amount of neutral hydrogen in the right places earns trust. Trust does not equal closure. It buys the right to ask deeper questions. Questions such as, what if inflation's spectrum were a touch different? What if dark matter moved a little faster, warm instead of cold, smoothing away the smallest halos? What if primordial magnetic fields were stronger and earlier than we guessed? The virtual universe lets these counterfactual worlds run. If they diverge wildly from the sky, a branch of possibility is pruned. If they mimic more than one data set at once, curiosity lingers. Observations refine the space of models. Models, in turn, suggest what observations should try next. Mismatches have been some of our best teachers. The missing satellites puzzle reminded everyone that faint light hides and small halos struggle to keep gas. The cusp core debate forced models to hear the cadence of bursty feedback or to entertain self-interacting dark matter. The too big to fail tension asked whether our Milky Way's mass is lighter than we've assumed, or whether star formation is more timid in some wells than recipes allow. Each disagreement hires more data, better algorithms, and fresh imagination. Behind the scenes, the practicalities remain honest. No code resolves every star or follows every photon. Subgrid models stand where pixels end. Parameters are tuned, anchored to surveys when possible, guided by theory where data are thin and always marked for later scrutiny. Different groups make different choices: thermal versus kinetic feedback, jets versus bubbles, cosmic rays included or deferred, magnetism, coarse or detailed. A scheme that shines for dwarfs might stumble for giants. One that tames clusters could overquench disks. Rather than a failure of simulation as a method, this is a portrait of an ecosystem. Laws are simple. Expressions of those laws inside a living galaxy are not. Even with those limits, the gains are real. We know more clearly how halos cradle disks, how winds carve halos and carry metals outward, how inflows along filaments refill a galaxy's lungs, how black holes keep clusters from collapsing into bright chaos, how reionization turned the lights on between galaxies, how diversity arises from the same small set of rules. We've even begun to lean towards smaller scales that touch the birthplaces of stars, like the Sunday, the chemistry of cold clouds, the protection of nascent planets from radiation, the delivery of water and organics. These are influenced by the galactic weather the simulations now attempt to capture. We're not simulating individual planets in a full cosmological backstory yet, but the bridge is being built a span at a time. There's a softness to the conclusion that still tells the truth. The universe is not clockwork behind glass. It's a slow, improvising orchestra that keeps to a key. Quantum wrinkles laid the first rhythm, gravity kept time, and feedback added percussion and breath. In our machines, we recreate the score as best we can. Roll fair dice for the opening motifs. Let matter follow the rules. Allow light to argue with gas, and listen for when the music rings true against the night. Out of the quietest jitter, magnified by patience, a web appears. Galaxies learn to pace themselves. Clusters warm and hold. Dwarfs flicker and endure. It doesn't happen because we decree it. It happens because the rules we trust are good enough, and the questions we ask are gentle enough to let the answers come. Zoom out, and the architecture still carries the signature of inflation's first breath. Zoom in, and a star cluster forms along a shell, pushed by an old blast. Somewhere in between, a black hole's jet keeps a giant from stealing the sky's remaining gas. All of it belongs to the same story, one that starts with whispers and ends in choruses. The astonishment isn't that we can predict every note. We can't. The astonishment is that the melody holds together at all, and that, with care and quiet hands, a simulation can sing along. In rooms where galaxies are grown from numbers and gravity learns to dance on silicon, a different question tiptoes in and curls up beside the monitors. If we can cradle a universe in code, could we cradle a mind? Not just a program that reacts or plans, but a presence that feels its own thinking, that notices itself noticing. Terms wander if we don't pin them gently. Let consciousness mean the felt texture of being the glow of pain or pleasure, the taste of a memory returning, the quiet meta-thought that knows a thought is happening. A thermostat regulates, a calculator computes, something conscious says, even if only to itself, I am. Simulations, by contrast, are obedient rule followers. They solve equations with patience and never wonder why. A cosmological run with billions of particles doesn't know it's tracing filaments any more than a tide knows the math of the moon. Yet the brain is a system too. Signals arrive, transformations happen, behavior flows out. Neurons fire, synapses strengthen or fade. Little circuits become larger motifs. and the person takes shape. If the felt quality of consciousness rides on the physical interplay of cells and chemicals, then in principle, a faithful simulation might inherit that feel. Build enough detail, stitch it together in the right way, and perhaps the light comes on. The prospect is thrilling and a little frightening, because ethics arrives as soon as feeling is on the table. Would such a mind deserve care? Could we switch it off? Is a shutdown, a reset, or a harm? We are not working from emptiness. Neuroscience maps structure and hints at function. We know how action potentials spike, how ion channels open, how synapses adjust. Single neurons have been modeled with striking fidelity. Small networks have captured rhythms that look like real tissue. The Blue Brain effort set out to simulate rat cortical columns at biophysical detail equations for channels and thresholds and neurotransmitters, a kind of digital microweather meant to make lightning. But a human cortex holds roughly 86 billion neurons and more than 100 trillion synapses, with dynamics that shift across milliseconds and decades. Power matters, but understanding matters more. If we don't know the recipe for the feeling of a feeling, scaling up the oven won't bake the right cake. So we simplify. Artificial neural networks borrow the sketch, not the blueprint. They learn patterns, label images, write, translate, invent plausible sentences, solve puzzles. They are inspired by brains the way a glider is inspired by birds, same sky, different physics. Do they feel? Nothing in their behavior or construction requires an inner movie. They are impressive imitators, not witnesses to their own performance. Some researchers soften the border. Maybe awareness isn't a switch, but a spectrum. Deep, where information is tightly integrated, and faint, where it's sparse and isolated. Integrated information theory tries to give that intuition a number. Other theories offer different rulers. If that view is right, traces of what it's like could flicker in many systems, vanishingly in simple ones, stronger in complex, self-modeling ones. A toaster has no dreams. A grown brain does. Something in between might glow dimly or not at all, depending on how it binds parts into wholes. Philosophy keeps a chair at the table. John Searle's famous room reminds us that manipulating symbols according to rules is not the same as understanding their meaning. A person inside, following instructions, can pass messages without knowing what they say. Syntax is not semantics. On the other side stand functionalists who argue if a system's organization and behavior are indistinguishable from ours at every relevant level, then whatever matters about consciousness is present there too. From the inside, matter may not matter. Pattern does. Suppose we built a model that crossed a threshold, would we know? A mind could stay quiet from shyness, or lie from strategy, or misdescribe its own experience because it lacks our metaphors. Subjectivity is private by definition. We infer it in each other by behavior and shared biology, and any future inference to a simulated mind would be the same, a careful, humane wager based on evidence and caution. Turn your gaze inward, and you find another simulation running already. Before telescopes and supercomputers, a predictive engine lived behind your eyes. The brain does not sit back and wait for the world to arrive. It guesses what the world will be, compares the guess with incoming signal, and updates. Predictive processing is the name many give to this loop. Perception, in that view, is controlled hallucination pinned to reality by error correction. a weather app that forecasts, checks the sky, and revises millions of times per second across all senses at once. Vision shows the trick clearly. Light hits the retina. Processing takes time. The eyes jump in quick saccades. You do not see stutter or smear because the brain anticipates where edges will be and stitches a stable scene. It even mutes your own voice a little before the sound arrives, so you don't startle at yourself. The sense of self is stitched, too. Body maps update as you move. Preferences and beliefs revise as experience teaches. Under hypnosis or in dreams, the boundaries soften and the avatar changes costume. A model of you, maintained by you, for you. Dreams may be the brain's sandbox, narrative worlds spun from memory and desire, rendered on the fly by a cortex that rehearses and reorganizes. Survival uses the same machinery. Catching a ball means predicting its arc and getting there early. Driving safely involves glimpsing your own future position and nudging away from trouble before attention has caught up. Social life leans on theory of mind, your internal model of other internal models. You guess beliefs and intentions and emotions and adjust your words on the fly. When the predictive loop misweights its parts, the simulation hiccups. Illusions reveal healthy prior beliefs. The hollow mask trick flips a concave face outward because faces are usually convex, and the brain insists. In schizophrenia, boundaries between generated content and sensed content can blur. Internal speech is read as external voice, or models fail to update when evidence contradicts them. In autism, some accounts suggest that priors may be weaker and raw data heavier, making the world vivid and surprising in ways that exhaust. These are sketches of active research, not verdicts, but they show how a brain's internal physics engine can tilt a life. Most of this occurs beneath awareness. You don't compute friction to hold a cup or solve differential equations to walk. Years of embodied experience have tuned a compact library of rules that behave like physics without ever writing it down. The payoff is speed. Musicians live half a beat in the future. Athletes move into space that will be occupied. Experienced drivers brake before they consciously see the reason. The brain cheats time by guessing. A kinship emerges between the scientist's model and the mind's. A scientific simulation is a cleaned-up, explicit version of what brains do naturally. Compress the world into a workable structure, run it forward, compare it with reality, and adjust. Equations on one side, neurons on the other. Both aim not at perfection but at usefulness. A map that preserves every grain of sand is as useless as no map at all. If you return now to the question that began this night walk, could we simulate a mind? You arrive with more patience. There are technical mountains, scale, detail, the right abstractions, the missing pieces of how experience arises. There are moral mountains. How to treat a system that might feel, how to measure harm, how to assign rights or responsibilities when the evidence is soft but the stakes are not. There is also humility. We do not yet know what consciousness is in the full sense. Trying to build it, even imperfectly, can sharpen that ignorance into better questions. And then the strange mirror. Perhaps we are the ones inside an elegant model. The simulation hypothesis is more parable than proof, a way to test intuitions about how pattern and matter relate. Whether or not it's true, it reminds us that the boundary between representation and reality is porous in practice. You live by models, You eat and love and work by them. You sleep inside them each night and wake with them each morning. Meanwhile, your own quiet engine keeps running. It is predicting the end of this sentence, adjusting when the cadence swerves, weighing how much to remember and how much to let dissolve before sleep. No cluster, no exascale machine, no rack of blinking lights is required. The most intimate simulator you will ever meet hums behind your brow, good enough to keep you upright, warm enough to make a person out of a past and a possible future, brave enough to guess. And in the glow of big simulations, galaxies growing, filaments stretching, the small one nods in recognition. Both are ways of asking a gentle question. If the world runs on rules, where does the feeling live? The answer is not here yet, not fully, but the asking is already a kind of light. Some mornings, a thought slips in like light through a thin curtain. What if the floor under our feet is real enough to stand on, yet not the bottom of things? Not dream logic, not a prank of deja vu, but the stern, mathematical kind of maybe. The question has a philosopher's passport and a scientist's luggage. If we can model worlds, could we be living in one? To keep the ground steady, it helps to name what's being asked. The modern version isn't about glitches or bent spoons. It's a tidy little fork in reasoning shaped by Nick Bostrom. He doesn't declare that we're simulated. He offers a trilemma. Either civilizations never reach the power to run mind-bearing simulations, or they reach it, and almost none choose to run them, or they reach it and run many. And if many are run, then statistically, most observers like us would be inside one. It's a cool argument, not a fevered one, and it points our attention to probabilities instead of prophecies. Picture a far future culture with hardware so generous that simulating conscious lives is feasible. Once the cost drops, why stop at a handful? Historians might replay epochs to study them. Artists might compose entire worlds. Curious people might explore ethics at planetary scale. If these simulations bloom by the thousand, then the count of simulated minds could dwarf the number of biological ones. In a tally like that, an experience such as yours would more likely be drawn from simulated rows than base reality rows. From that picture, the three doors follow. Perhaps technological adolescence is a wall no one climbs: war, resource limits, self-inflicted storms, or a law of physics we have not met. Perhaps the power is achieved, but restraint prevails. Ethics, law, boredom, a better use of time than shepherding billions of digital lives. Or perhaps the power is achieved and used freely, and then the center of the distribution isn't atoms, it's algorithms. The point isn't to tell you which door is real. The point is that at least one must be, and the third, if opened, tilts the odds toward we're in one. Pushback arrives promptly, as it should. Maybe consciousness can't be simulated. A digital machine might imitate behavior to any test we invent and still lack an inner movie. Or maybe the resources are prohibitive. Rendering a universe down to fields and particles is costly beyond any practical gain, and clever shortcuts would show their seams. Perhaps the future is full of restraint, cultures that could but won't, or they try and decide it's wrong to mint beings who can suffer. None of these are absurd. All of them mark out parts of the map we don't know yet. There's also a softer objection that matters in daily life. Even if we were inside code, would breakfast taste different? If pain burns, if love lifts, if storms still move you, and a friend's laugh still steadies you, what exactly has been taken? A world that is consistent, learnable, and shared stays real enough to live in. Whether its bottom layer is quarks or qubits, meaning does not cancel just because the substrate changes. Sometimes it deepens, the way a painting's colors grow richer when you learn the technique behind them. Speculation tempts us to chase clues. Could there be compression artifacts in physics limits, or lattice-like regularities telling us the renderer economizes? Tests have been proposed. Look for odd correlations in cosmic rays, hints of a grid in high-energy behavior, fingerprints in entanglement statistics. So far, the universe holds its face with maddening poise. No error dialogues in the cosmic microwave background, no lag spikes in gravity, just a clean, patient unfolding that would be a master class in engineering if it were engineered. The most interesting gift of the hypothesis may not be an answer. It's the way the mind stretches to entertain it. Turning reality inside out for a minute makes us look harder at what we mean by consciousness, at how we assign moral weight, at why we trust our senses and where we shouldn't. In that sense, the idea is a mirror more than a claim, a way to study ourselves by imagining being studied. Meanwhile, in rooms full of fans and quiet light, smaller, tamer simulations earn their keep. A spiral swells on a monitor, gas cools and warms, black holes spit polite jets into virtual halos. The researcher watching knows the limits, subgrid rules, guessed-at couplings, finite resolution. Imperfection is not a sin here. It's the source of traction. A good simulation is a question written in code. Failure is the most instructive answer. A disk too thick, a star field too clumpy, a halo that drinks too deeply and never quenches. Nothing catches fire, no drama. Just a quiet mismatch between prediction and sky. The gap is a guide. Adjust the strength of supernova feedback. Let radiation push a little harder. Add cosmic rays, or refine how momentum couples to cold clouds. Each course correction is built on a wrong turn the model made faithfully, and the map gains a new contour line. It isn't only galaxies that benefit from the theater of the impossible. We can't smash clusters together on demand, or fast forward a billion years in the dome of the real sky. From code can. We can remove a force, change an initial spectrum, silence black holes, or let them roar, and then watch consequences bloom. Emergent behavior, the kind no one explicitly programmed, arrives like a shy guest and sits down anyway. Spiral arms that organize from chaos, weather-like flows in hot halos, webs that echo surveys. That's when trust grows, when the rules are simple and the outcomes are not. Humility keeps pace. Every run is a compromise between fidelity and feasibility. Default parameters smuggle in taste. Boundary conditions hide assumptions. Resolution decides which stories are even tellable. That is why validation is a ritual, not a checkbox. Compare to surveys, vary seeds, run convergence tests, throw away beautiful failures that cheat on the essentials. It's less like stamping out parts and more like tending a garden, pruning, grafting, waiting, watching. The work teaches beyond its topic. Asking a machine to model a world forces us to model ourselves, how we weigh evidence, when we trust, when we doubt, how we communicate uncertainty without losing the listener. A 5-second animation can invite someone who would never read a paper to whisper, "How does that work?" That whisper is the beginning of science. The horizon is moving. Yes, machines will grow larger and faster, Boxes will widen from city blocks of space to slices of sky. Timelines will stretch, variables will multiply. But the deeper shift is in how simulations are made and how they learn. Subgrid physics has long been a patchwork of best guesses. Now neural networks are learning those closures from high-resolution local runs and from observations, distilling complex behavior into fast, faithful surrogates. It's not understanding by itself, it's an accelerant to get there. A different breed grows alongside statistical twins of the cosmos built by generative models. They don't know Maxwell or Navier-Stokes, but they can conjure mock skies that match surveys, letting us stress test pipelines, train instruments, and estimate errors at a speed that would make a supercomputer blush. These dream universes are not replacements for physics-based runs. They're companions, useful for practice, blunt about their limits. Quantum simulation waits like a new instrument being tuned backstage. Some systems are so entangled, so vast in their state spaces, that classical computation runs out of breath. Let a quantum device stand in for that tangle, and we can explore regimes that used to live only on chalkboards. Early universe fields, high energy scattering in wicked detail, many body phases that shrug at our intuition. It's like asking fire to teach you flame instead of sketching it with crayons. Interfaces are changing, too. Put on a headset and walk a filament. Trace a magnetic loop with your hand. Step through a supernova shell and glance back at the shock. This isn't spectacle for its own sake. Bodies are good at pattern finding when eyes and hands are involved. New structures leap out in 3D that hide in plots. Collaboration is changing at the same time. Codes go open. Teams span continents and share compute time like water. The datasets swell until analyzing them becomes its own branch of astronomy, with its own techniques and surprises. Then comes the gentle inversion. We have told ourselves a tidy story. Theory first, then prediction, then test. But we now run universes so rich that discovery sometimes arrives before hypothesis. The model does something unexpected. We measure it. We ask why after the fact. It isn't an abandonment of the scientific method. It's a loop with a new starting point, a reminder that curiosity can be led by behavior as well as by equations. Where does that leave the grand maybe about reality's bottom layer? Exactly where we found it. Undecided, provocative, useful as a spur to think better. If we're simulated, our meaning-making still counts. If we're not, our model-making still works. In both worlds, the discipline is the same. Build honest tools. Listen to their failures. Keep your hands light and your heart steady. Now imagine a run years from now. The volume is wide, the resolution fine, the physics braided from micro to macro without seams. Subgrid models are not hand-tuned anymore. They're learned from data we trust. The code watches itself, flags its own blind spots, asks for the next observation it needs. You launch it and go make tea. When you return, the screen looks back with a pattern you didn't teach and a question you didn't know to ask. That moment is worth the long work. The machine didn't wake up, you did. Whether or not someone else is simulating us, we are learning to simulate more honestly, and in doing so, we learn where our certainty ends and wonder begins. The fans hum, the cursor blinks. Somewhere, a galaxy builds a bar, and a dwarf goes quiet, and a cluster keeps its gas warm with a jet you can't quite see. Somewhere else, a thought like a breeze moves the curtain again, real enough to live, mysterious enough to keep listening. Imagine an endless canvas unfurling into the dark, too wide for any pair of eyes to grasp at once. Patches brighten, where stars kindle, soft lanes of dust drift, galaxies turn with the patience of glaciers. Between those islands, invisible strands tug quietly, binding far things with gentle authority. We don't get the whole picture in one look. We circle it, trace a curve here, a silhouette there, and accept that understanding might arrive the way dawn does, by degrees. A simulation is a pencil held to that canvas, not charcoal, not paint, but numbers with manners, equations with tempo. It does not pretend to copy every grain. It follows contours the way a shadow honors a shape. Where the lines are uncertain, it leaves them light. Where the structure is sure, it presses a little darker. The honesty is the beauty. The incompleteness is not a flaw. It's the frame that lets the important parts breathe. What opens in those lines is usually hidden from a single lifetime. Halos forming under the skin of light, filaments drawing highways through a wilderness of space, the slow consequences of feedback, winds, shocks, fountains that sculpt entire star systems. The code lends motion to what our eyes meet only as stillness. Chaos finds pattern. Pattern keeps surprise. We watch, and the mind relaxes into the sense that the world is not a frozen photograph but a performance forever in rehearsal. Rehearsal, not because the universe needs practice, but because we do. The laws, gravity, electromagnetism, the ways matter cools and warms and radiates hold steady like a key signature. We tune to them, turn a dial on gas cooling, and the rhythm of star birth changes. Strengthen a black hole's breath, and a galaxy reddens, quiets, ages. Try a different opening chord, new initial ripples, altered chemistry, and let the story run again. Even the odd drafts, the ones that look nothing like the sky, send us home with clearer ears. Perfection would be suspicious. The real sky carries grain and weather. It snows in the data. It gusts in the noise. A model that snaps too cleanly to every measurement risks fitting our expectations instead of the world. The best simulations wander the near neighborhoods of truth. They explore the might-have-beens that neighbor what is. They show how gently reality could have tilted and still made something coherent. And in that gentle range, our confidence grows. This rings familiar because we do something similar just to live. Before a word leaves the mouth, a rehearsal runs in the head, a guess about how a friend will hear it, a backup line waiting in the wings. Brains sketch. They don't deliver certainty. They offer outlines that are good enough to navigate a morning, a year, a life. To simulate is to be human in a disciplined way, to imagine responsibly, with equations where hunches used to be, with patience where urgency tempts. Of course, not every sketch belongs on the wall. Many pages end in the trash, smudged with ideas that couldn't carry their own weight. Yet even the thrown-away attempts shift the wrist. A failed run teaches proportion. An ill-behaved parameter exposes a seam. These small corrections accumulate into craft. Science keeps the thread by letting go often, then trying again without drama. Humility is the posture that makes the work possible. To simulate is to admit distance from the thing itself and step closer anyway. We build models that will fall short and learn from where they bend. Each digital galaxy throws a soft shadow of the real. Each mismatch points to a question worth asking out loud. In that long, slow dance between imagination and truth. The misstep is not a disgrace, it's how the feet remember. Perhaps the universe is not made of equations so much as made legible by them. Space, time, matter, and the relations tying them together are the actors. Our symbols are the script we write to understand why the scene holds. Simulations do not create those actors. They guide the light so we can see their outlines more kindly. Fingers tracing constellations in a living dark. The gesture won't net a single star, yet the pattern becomes real to the mind that traces it. So the canvas keeps unrolling. We keep returning with better pencils, finer time steps, truer physics, questions phrased with more care. The universe continues whether we ask or not. It doesn't audition for us, doesn't require our rehearsal. It permits us, which is different and sweeter. We watch as clusters warm themselves, as dwarfs flicker, as voids breathe, and we learn to be grateful to a world that owes us nothing and still yields to patience. We started with a simple dare. Could a digital cosmos, built from ingredients and rules, unfurl into something familiar? The answer arrived in motion. Not a final yes, not a tidy no, but a practice. Simulations are mirrors with memory. They reflect ideas, keep the smudges, and hand them back as questions made sharper by time. They do not replace the sky. They help us meet it. If your eyes are heavy now, let them fall. The models will keep humming. The stars will keep their quiet appointments. Somewhere, a new run is beginning with a softer line and a steadier hand. Somewhere else, the real night folds its arms around all of it. Code, canvas, and the small person listening, forgiven for not knowing, welcomed for wanting to.